June 27, 1944, northern Saipan. The sun had barely risen above the jagged volcanic ridge when a team from the U.S. Marine Corps Signal Battalion came upon what looked, at first glance, like an ordinary metal trailer battered, scorched, its wheels half buried in coral sand. A closer look revealed something far more remarkable. On its side, stenciled in fading white paint, were the words SCR-584 radar set. Inside, the panels were intact, the scopes still faintly glowing, their dials marked with precision the Japanese engineers who later examined it could scarcely imagine. The Marines didn't realize it at the time, but they had just stumbled upon one of the most sophisticated pieces of electronic equipment ever built. An American mobile radar system capable of tracking aircraft and shells with unheard-of precision. The radar had been abandoned in the chaos of battle after its crew was killed during a nighttime bombardment. Its interior smelled of ozone and machine oil, the last trace of the men who had operated it. A few rounds had punched through the casing, but the heart of the system, a spinning parabolic dish, servo motors, and a bank of vacuum tubes, remained intact. The SCR-584 was the result of a collision between mathematics, microwave physics, and wartime urgency. Developed by MIT's radiation laboratory barely 3 years earlier, it could lock onto a target automatically and track it through cloud or darkness with an accuracy of less than 0.1 degrees. It was the radar that guided anti-aircraft guns to shoot down V-Aden flying bombs over London, the one that made night skies measurable and predictable. For the men who captured it on Saipan, it was just another piece of war junk to be shipped back to the engineers for analysis. For the Japanese who would eventually see it, it was a revelation. Word spread quickly through the captured Japanese technical units and forward intelligence officers. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Within days, a team of engineers from the Imperial, Japanese Army's Air Technical Research Institute, was dispatched from Tokyo to Saipan. Among them was Captain Yasuji Sato, a soft-spoken electrical engineer trained at Tohoku Imperial University, whose expertise lay in microwave propagation, though Japan had little practical equipment in that frequency range. Sato had spent the previous 2 years trying to build a G-centimeter wave radar capable of detecting B-29 with limited success. When he saw the SCR-584, he realized instantly that it represented a level of precision they had only theorized. The Americans, for their part, had no idea that their abandoned radar would become the object of intense foreign study. The SCR-584 was not meant to be captured. It was meant to operate behind secure lines, shielded by infantry and secrecy. But war was chaos, and Saipan had collapsed into an inferno of artillery and desperation. The Marines photographed the device, stripped it of its tubes, and shipped the remains back to the Signal Corps depot at Guam. But a detailed technical manual, one that outlined its automatic tracking system, had been seized by Japanese troops a few days earlier, during a brief counterattack near Aslito Airfield. That document would soon find its way to Tokyo. By August 1944, Sato and his colleagues were poring over diagrams of servo amplifiers, power waveguides, and the automatic tracking circuitry that made the SCR-584 unique. Their own radars, the Type A and Type II model Jeden, were primitive by comparison, operating at meter wavelengths, too coarse to track individual aircraft, and requiring constant manual adjustment. Japan's electronics industry simply lacked the magnetrons and stable oscillators that made the American system possible. It is like comparing an abacus to a calculating machine, Sato wrote in his notebook, recovered decades later from a private collection in Kanagawa. In the months that followed, as Tokyo burned nightly under B-29 raids, Japanese engineers would attempt to recreate portions of the SCR-584's design. They succeeded in building components that mimicked its rotation and elevation controls, but could never replicate its brain. the complex feedback loops that allowed it to lock on to a moving target automatically. It was the first time Japanese scientists truly grasped how far behind their wartime electronics had fallen. What began as a scorched trailer in Saipan's coral sands would ripple through Japan's technical consciousness. For Sato and his team, the captured radar was more than a weapon. It was a glimpse into another industrial universe, one that measured war not in courage or sacrifice, but in microseconds. They would spend the rest of the war chasing that precision, and never quite catching it. In a dimly lit laboratory on the outskirts of Tachikawa, just west of Tokyo, a group of engineers gathered around a table stacked with fragments of a metal chassis and rolls of technical diagrams that had been smuggled in from Saipan. It was September 1944, and the war had already turned against Japan. The B-29 had begun their methodical incursions over Kyushu and Honshu. Yet here, under the flicker of unreliable electricity and the low rumble of distant air raid sirens, a handful of men were attempting the impossible. To understand a radar so far beyond their reach, it might as well have come from another planet. Captain Yasuji Sato stood in silence as the team unrolled a schematic labelled Servo Synchronization Circuit Antenna Tracking Assembly. The American terminology baffled them. The document was dense with English abbreviations: AZ gyro, ELEV servo, stab feedback, none of which had any clear Japanese equivalent. They had linguists, but few had the engineering background to translate not just the words, but the concepts. It wasn't enough to copy the machine, they had to think like the people who built it. The SCR-584's secret lay in its closed-loop feedback system, something only a handful of Japanese engineers even understood in principle. It used a combination of servo motors and vacuum tube amplifiers to automatically align its antenna to a moving target, updating its position hundreds of times per second, in the US. Such control theory had matured in the laboratories of MIT and Bell, nourished by an industrial ecosystem that could produce thousands of precision resistors and capacitors per day. Japan's own vacuum tubes, by contrast, were unreliable, impure glass, inconsistent filaments, prone to failure after hours of use. Sato's deputy, Lieutenant Commander Harada, had once built a prototype radar using salvaged radio parts from civilian sets. It barely worked beyond a kilometre, yet now he found himself tracing the logic of a system capable of guiding a 90 anti-aircraft gun to within meters of a bomber flying at 0 feet. He stared at the hand-drawn diagrams and whispered, "They have made mathematics move." Tokyo's reverse engineering division, formerly known as the Rikugun Koku Gijutsu Kenkyujo, Army Aeronautical Technical Research Institute, had been tasked with replicating the Seimaya, SCR-584, but their work faced impossible constraints. The supply of copper had been diverted to aircraft production, aluminum was scarce, and every transport route to Korea and Manchuria was under threat from Allied submarines. Each resistor had to be handmade, wound by female workers using whatever wire they could scavenge from civilian power sets. Sato recorded in his log that their first attempt to replicate the automatic tracking system failed catastrophically. The servos oscillated uncontrollably, spinning the antenna until it tore free of its mount. They didn't have oscilloscopes accurate enough to measure the instability. Their substitute magnetron, developed at the Navy's Yokosuka laboratory, operated at 10 centimeters instead of 3, too coarse for fine resolution. The feedback loops couldn't stabilize. By late 1944, Tokyo's nights were illuminated by firestorms. Yet the radar team continued their work beneath blackout curtains, often sleeping on the floor beside their benches. In one surviving diary entry, Harada wrote, "The Americans wage war by the decimal place. We wage it by the heartbeat." Even as their research faltered, they came to appreciate the deeper meaning behind the SCR-584. It wasn't just a machine, it was a philosophy of precision, a statement that victory came from measurement, not intuition. In the imperial system, hierarchy often silenced innovation. In the American system, A junior engineer could challenge a colonel's design if the math proved sound. That difference echoed through every circuit Sato studied. By February 1945, as the first firebombing raids consumed the Tokyo suburbs, Sato's laboratory was evacuated to Nagano. The SCR-584 diagrams were packed into a wooden crate marked Fragile Radio Components. They carried with them a half-assembled replica, an awkward contraption of misaligned servos and flickering tubes that barely functioned. Yet when Sato looked at it, he saw something more than failure. He saw a mirror one that reflected not Japan's weakness, but what modernity truly required: trust in precision, faith in measurement, and freedom to question authority. When the war ended 6 months later, the prototype was buried under the rubble of a burned factory, but its lessons would not vanish. In the ashes of defeat, those same engineers would one day rebuild Japan's entire electronics industry, guided by what they had glimpsed inside that impossible American radar. The war had ended not with a bang, but with a long mechanical silence. When the air raid sirens stopped and the static of surrender faded, Japan became a land of quiet factories and broken circuits. By early 1946, American occupation forces began arriving in waves, not with rifles drawn, but with notebooks and engineers. They came to dismantle what remained of Japan's military technology, to document its extent, and to understand how close or how far the empire had truly come. For Captain Yasuji Sato, now a demobilized civilian in patched clothes, the visit of American technical officers felt like a ghost returning to claim its own invention. The Nagano lab had survived the final raids, though stripped bare. Its benches still bore the scorch marks of burnt diagrams, its floors littered with shards of broken vacuum tubes. When the Americans came men from the Signal Corps and the Scientific Intelligence Division, they spoke in rapid English, photographing everything, tagging equipment, and taking notes on captured radar sets. One of them, a young engineer named Lieutenant Harold Mitchell, paused over a pile of fragments that had once been the replica of the SCR-584. "You tried to rebuild this?" he asked gently, through an interpreter. Sato hesitated before nodding. Mitchell smiled faintly, not mockingly, but with something like respect. "It took us a whole team at MIT to get it working," he said. "You must have been close." That single word, close, lodged in Sato's memory. After months of silence and humiliation, it sounded almost like acknowledgement. In the months that followed, the American occupation authorities began quietly recruiting Japanese scientists for civilian research. Under the watchful eye of SCAP's Scientific and Technical Division, they converted former military laboratories into centers for telecommunications and electronics. Sato was invited unofficially at first to assist in translating technical manuals for post-war industry. It was menial work, but it gave him access to something extraordinary. Declassified American engineering documents, including the full specifications of the SCR-584 radar. For the first time, Sato saw the complete design, the feedback equations, servo constants, and gain control parameters they had once guessed at, through burned fragments. It was all there, laid out in clean typeface and annotated diagrams. The more he studied, the more he understood that the machine's brilliance did not lie in its complexity, but in its discipline. Every circuit was optimized, every feedback path measured and verified. It was an architecture of precision, born from an industrial philosophy Japan had never possessed. In 1947, Japan's first new research cooperative was formed, the Japan Radio Company Reconstruction Association. Many of Sato's wartime colleagues joined former radar officers, telegraph engineers, even mathematicians, once tasked with anti-aircraft prediction tables. They met in bombed-out warehouses and worked on salvaged benches, designing radio transmitters and oscillators for civilian use. To them, radar had become more than a military technology. It was a symbol of a new way to think. Sato often told his apprentices, "We once built machines that followed orders." Now we must build machines that follow truth. He taught them the mathematics of feedback, how a system could correct itself through error. A circuit must learn to disagree with itself, he would say, tracing loops of voltage on the chalkboard. To younger engineers, his words sounded almost philosophical, but Sato was dead serious. He had learned from the SCR-584 that the future belonged to machines that could measure their own mistakes. By the end of 1948, Japan's electronics industry was stirring back to life. Former military research labs became incubators for companies like NEC, Toshiba, and Hitachi, all rediscovering precision under new purposes. American advisors, once occupiers, became collaborators. Lieutenant Mitchell, now a civilian consultant, visited Sato's team that autumn. "Funny thing," he said, gesturing toward a newly built oscillator. "You're building what we'll need for our next generation of radars." Sato smiled faintly. "Then perhaps," he replied, "defeat is another kind of invention." For him and his peers, the ashes of war had given birth to something rarer than victory, a new understanding of how nations rise not by conquest, but by calibration. The lesson of the SCR-584 was no longer military, it had become moral. By 1949, Japan hummed with the low electric murmur of rebirth. Radio repair shops sprouted among the ruins, their windows lit with the soft glow of vacuum tubes scavenged from military stockpiles. Once, these tubes had guided anti-aircraft guns and radar dishes. Now they powered home receivers, police transmitters, and makeshift public loudspeakers. The country that had once measured its worth in tonnage of steel and shells was learning to measure in frequencies and hertz. For Yasuji Sato, it was a strange kind of resurrection. The man who had once built radar to detect death now taught factory apprentices how to tune life back into the air. At a small research division that would later merge into Tokyo Shibara Electric Toshiba, he worked with a handful of surviving engineers to design Japan's first stable shortwave oscillators for civilian. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now back to the story, slicing through the dark. But now there was no enemy, no fear, only the endless, patient search for accuracy. He realized that in perfecting machines, Japan had found a way to heal without forgetting. By 1963, the system was operational. Civil aircraft landing in Tokyo, Osaka, and Nagoya were guided by equipment bearing the same principles once buried in a jungle lab at war's end. The Americans who visited to inspect it marveled at the precision of its components, the silence of its servos, the clarity of its echoes. 1US. Colonel remarked half-jokingly, "I think you folks finally beat us at our own math." Sato bowed slightly. "Oh," he replied, "we just learned to listen more carefully to the noise." At home, Sato's health began to falter. His hands trembled when soldering, his breath shortened climbing the stairs to his office, but he continued teaching, dictating papers, mentoring graduate students who were building the first Japanese computers. He often sat beside them as they programmed early logic circuits, his old eyes tracing the binary code scrolling across paper tape. "This," he would murmur, "is the new form of feedback. The machine now speaks its own language." In 1964, as the Shinkansen bullet train made its inaugural run to Osaka, Sato watched from a platform near Shinagawa Station. The train's sleek nose glinted in the afternoon sun, vanishing down the track at 210 kilometers per hour. The timing was perfect: arrival, departure, synchronization, all measured within fractions of a second. Around him the crowd cheered, but Sato simply nodded, feeling tears gather behind his glasses. It was the ultimate expression of what he had believed all along, that precision was not merely mechanical, it was moral, social, human. A train that never arrived late was a country that had learned to measure time as an act of respect. That evening, back in his apartment, He opened his wartime notebook one last time. The pages were yellowed, the ink fading, but the formulas remained: feedback ratios, gain margins, phase corrections. At the very back, in the margins beside his old drawing of the rate error amplifier, he wrote a final note in careful English. The enemy was never the machine. The enemy was our ignorance of what the machine could teach us. He closed the book and set it beside his radio, which softly hummed to life with an NHK broadcast. A young announcer spoke of the coming 1964 Tokyo Olympics, of Japan's miraculous recovery, of technology as the nation's new face to the world. Sato smiled faintly. The world would see the cameras, the trains, the computers, but not the quiet circuit beneath it all, the ghost that connected defeat to mastery. Only he, and perhaps a handful of others, would remember that the heartbeat of modern Japan had once been captured in a muddy clearing on Saipan. In April 1965, Sato died quietly in his sleep. On his desk, his students found the photograph Harold Mitchell had sent the American radar trailer under a pale sky, and beside it, a small note in Japanese. "We copied what we feared, until we understood what we admired." His ashes were scattered near the mountain lake at Nagano, where his wartime lab had once stood. The pines had grown thick again, and the wind hummed through the branches like static. A few of his students buried the tin box beside the water, sealing within it a strip of magnetic tape from the new computer they had built, a symbolic continuation of the signal. Years later, one of those students would become chief engineer at NEC, designing Japan's first integrated radar computer guidance network. When asked where his inspiration had come from, he simply said, "From a man who taught me that precision has a memory, but as the invisible architecture of peace." The circuit had closed, perfectly balanced. What was once captured became the cornerstone of an empire rebuilt not through conquest, but through calibration. In the end, Yasuji Sato's prophecy had come true. Machines did not think like men, they thought better, because they remembered. And in their quiet, tireless measurement, they carried the memory of a nation that had once learned through ruin how to make its own rhythm match the heartbeat of precision. In the decades that followed, Japan's hum grew louder. The 1970 brought color televisions, calculators small enough for a shirt pocket, and the world's first microchips stamped "Made in Japan." Each innovation was a pulse of that same rhythm: order, measurement, refinement. Sato's name faded from public memory, but his students quietly carried his ethos into every circuit and servo they built. At the National Science Museum in Ueno, a small exhibit opened in 1973 titled "Origins of Japanese Electronics." Among the glass cases stood a preserved American radar amplifier, its serial plate still marked SCR-584. Most visitors passed it without a glance, drawn instead to the glittering displays of Sony radios and Toshiba semiconductors. But one old man, a former student of Sato's, lingered before it. He studied the wires, the transistors, the brass fittings dulled with age. Then, in the reflection of the glass, he saw the Tokyo skyline behind him glowing, alive, measured in perfect rhythm. He smiled. "It's all still running," he whispered. "The loop never broke." Outside, the city pulsed with invisible frequencies, radar, radio, control signals, all descendants of that captured machine. In every transmission, a fragment of Sato's legacy persisted. That to understand technology was to understand humility. That the truest precision was not domination, but awareness. As night settled over Tokyo Bay, cargo ships and aircraft traced their routes through the air, their paths guided by unseen waves. Somewhere within those, signals between noise and clarity, defeat and mastery, the ghost in the circuit still whispered, patient and exacting. The war had ended 20 years ago, but the feedback loop Sato began continued, unbroken, carrying forward the one lesson he had left behind. That progress, like radar itself, is only possible when you keep listening for the echoes. Broadcasting. The laboratory was primitive. Cracked windows, soot-blackened walls, and benches made from warplane wings. But in that room, surrounded by salvaged equipment, they discovered a new form of patriotism, the pursuit of precision for its own sake. It was in early 1950 that an American magazine arrived by diplomatic mail, sent to Sato by Lieutenant Harold Mitchell, now working for RCA in New York. Inside was a feature titled The Coming of the Transistor Age. Sato could barely believe what he read. The Americans had created a device that could replace vacuum tubes entirely, a crystal of germanium that switched current faster, smaller, and cooler than anything before. It was as if the evolution of radar had found its next step, and once again, Japan was behind. Yet unlike 1944, this time Sato saw opportunity instead of despair. He called his small team together and read aloud from the article. "The transistor," he said, "is the child of feedback. It learns from its own signal." The connection was more than metaphorical. The SCR-584 had shown him that progress began when machines could self-correct. The transistor, he believed, would do the same for nations. That year, he wrote a short internal paper titled On the Principle of Small Corrections. It argued that Japan's recovery depended not on massive projects or monumental inventions, but on incremental perfection, the continuous reduction of error. The Americans built the SCR-584 through networks of measurement, he wrote. "We must now build our piece the same way each resistor, each circuit, each mind calibrated to truth." By 1951, Japanese firms began experimenting with germanium diodes supplied by American companies under the post-war reconstruction agreements. Sato's group joined a cooperative research project between Toshiba, NEC, and the University of Tokyo to build the country's first domestic transistor. They lacked the cleanrooms or pure materials of Bell Labs, but they compensated with ingenuity. Using sake alcohol as a cleaning solvent and fine silk for wire brushes, they coaxed a handful of prototypes into life. One transistor lasted 12 hours before burning out, but it worked. In those moments, Sato would recall his wartime laboratory, the unstable servos, the screeching circuits, the smell of ozone. Now, that chaos had given birth to order. A nation learns, he told his students, the way a circuit does through failure. At night, he sometimes reread his wartime notebook, the one that had survived in a tin box buried under the Nagano lab. The paper had yellowed, but the English letters rate error amplifier remained clear. He traced them with a trembling finger and smiled. This, he whispered, was the beginning. By 1952, Japan was no longer under formal occupation. Its factories were alive again, its engineers respected, its people curious. In Osaka, young technicians assembled the first experimental televisions. In Yokohama, a startup called Tokyo Tsushin Kogyo, soon to be renamed Sony, demonstrated a prototype tape recorder using circuitry descended from wartime radar amplifiers. The transformation was astonishing. In less than a decade, the same scientific minds that had once reverse-engineered American radar were now exporting radios back to the United States. The feedback loop of history had closed upon itself. For Sato, the lesson of those years was simple but profound. Precision, once a tool of destruction, could become the language of creation. Every dial tuned, every waveform stabilized, was a small act of redemption. And in that quiet act inside every transistor, every radio, every flickering TV set, lived the echo of a captured radar from Saipan, still teaching Japan how to measure the future. The winter of 1953 arrived with the sound of radios, not sirens. Japan was no longer a silent, blacked-out nation, but a country wired together by static, music, and the hum of circuitry. What had begun as a desperate act of post-war survival was becoming something larger, a national identity built around precision. Factories that once made shells now built capacitors, Foundries that had forged propellers now shaped transistors. In Tokyo's Kawasaki district, where the skeletons of old aircraft hangars still stood, Yasuji Sato visited a new facility bearing a modest sign. Sony Research Laboratory. Inside, he found rows of young engineers bent over benches, their faces lit by the soft glow of soldering irons. The air smelled of flux and ambition. They were building Japan's first portable tape recorder, a device that would carry voices across oceans. When Sato was introduced as a radar engineer from the old war, the room fell silent with awe. Many of these engineers had studied his post-war papers on servo control and frequency stability. To them, Sato represented the generation that had turned defeat into measurement. The leader of the lab, a sharp-eyed man named Masaru Ibuka, greeted him with enthusiasm. "We stand on your shoulders, Sensei," he said. "Without the radar men, we would still be building radios by instinct." He had long since learned that real progress came not from genius, but from calibration, from the endless refinement of small errors. As he walked through the lab, he noticed a test bench where a prototype amplifier flickered erratically. The young engineer apologized. "The gain loop is unstable, sir." Sato chuckled softly. "Then teach it to argue with itself," he said, repeating his old maxim. Moments later, the engineer adjusted the feedback resistor, and the signal steadied into a perfect sine wave. That was the spirit of the new Japan feedback as philosophy. Across the country, the principles once confined to radar tracking and fire control servos were now reshaping industry. Servo theory guided camera shutters at Nikon. Automatic control loops regulated temperature in steel plants. Even textile machines borrowed from radar feedback circuits to maintain tension and speed. What had once been a desperate wartime imitation of American technology had become a culture of precision all its own. In 1954, Sato joined a national advisory board formed under the Ministry of International Trade and Industry. Its mission, to establish standards for electronic components and promote export-quality manufacturing. For the first time, Japanese engineers were not copying, they were defining. Sato's name appeared on the first Japan Industrial Standard for oscillators and frequency control, a modest but symbolic milestone. The nation that had once marveled at American servos now exported its own. Still, Sato's thoughts often drifted back to Nagano, where the buried fragment of the SCR-584 slept beneath the soil. He sometimes wondered if progress had truly erased the memory of failure or merely transformed it into something else. During a meeting in Osaka, a young reporter asked him, "Sensei, do you ever regret studying instruments of war?" Sato thought for a moment before answering, "Regret? No. We studied the language of precision, and that language does not know war or peace. It only asks, how accurate can truth be?" By 1955, Japan's electronics exports were doubling every year. Transistor radios appeared in shop windows, their polished chrome and glass, a symbol of national rebirth. In their circuits lived the DNA of radar tiny feedback loops, gain controls, oscillators that once listened for bombers now singing music through headphones. That summer, Sato visited the new NHK Broadcasting Center to see Japan's first television broadcast. As the image flickered to life, a baseball game from Meiji Jingu Stadium, he felt something stir within him. The clarity of the signal, the harmony of the picture. It was, in a quiet way, what his wartime radar had always tried to achieve. Tracking motion, capturing precision, turning chaos into comprehension. When he stepped outside into the bright Tokyo evening, the streets glowed with neon. In each sign, each transmission, he saw reflections of the machine that had changed everything, a captured radar from a battlefield now reborn in the circuitry of peace. The nation had learned to lock onto the future, one signal at a time. By 1957, Japan had grown unrecognizable to those who had seen it burn. Neon bled into the night air over Shinjuku. Transistor radios crackled in streetcars. Factories hummed with a steadiness once reserved for prayer. For Yasuji Sato, now 51, the rhythm of this new Japan sounded like vindication, the steady pulse of feedback made flesh. He often told his students that a nation could be tuned like a circuit, that perfection was not a point but a process. Yet beneath that optimism lay something else, a faint hum of unease, the sound of ghosts buried under progress. In a lecture at the Tokyo Institute of Technology, Sato wrote 3 English words on the chalkboard: feedback, control, learning. To measure is to remember. He paused, looking at the rows of young engineers' children when the war ended, fluent now in the language of oscilloscopes and transistors. You must never forget, he said quietly, that our precision was born from loss. Every stable waveform you see here was paid for in ruin. The room fell silent. They did not fully understand, but they felt the weight of it. Sato had become something of a living relic in the new industrial order. He still wore his old army spectacles, still carried his battered notebook from the Nagano days. Yet companies sought him out constantly. Toshiba consulted him on control systems for automated assembly lines. Matsushita invited him to Osaka to advise on transistor miniaturization. He saw in these factories the culmination of everything he had once struggled to imagine: servo systems aligning robotic arms, automatic test benches correcting their own measurements, machines learning from their errors without human touch. During one visit to Matsushita's plant in Kadoma, a young engineer demonstrated a prototype that measured current drift and adjusted its gain in real time. It finds its own zero, the man explained. Sato nodded slowly, recognizing the principle instantly. It was the SCR-584 soul, reincarnated in a consumer amplifier. He felt a shiver pride mingled with melancholy. It remembers, he murmured. The machine remembers. In private moments, Sato began to write essays reflecting on what he called the ghost in the circuit, his term for the hidden continuity between destruction and creation. Every feedback loop, he wrote, contains a memory of its own instability. It knows what it was before it learned to balance. To him, this was not merely electrical theory, but moral philosophy. A society that ignored its errors could never stabilize. A nation that measured its past honestly could predict its future. His students adored him, though many found his tone haunting. "Sensei," one asked, "do you think machines will ever think like us?" Sato smiled. "No," he said. "They will think better because they will not forget their mistakes." That autumn, Sato received an unexpected letter from the United States. It was from Harold Mitchell, his old acquaintance from the occupation years. Inside was a photograph of a sleek white trailer with a parabolic dish on its roof, the new AN MPQ G-Shinch radar. "You'd recognize its grandfather," Mitchell had written. "We're still chasing perfection, just faster now." Sato placed the photo on his desk and stared at it for a long time. The angles, the symmetry, it was the same lineage, an echo of the machine once captured at Saipan. Only now, the imitation flowed in the other direction. Japan's components, its tubes, resistors, precision capacitors were being sold to Americans who had once seemed untouchable. One evening, Sato returned to Nagano to visit the ruins of the old wartime laboratory. The forest had grown thick around the site. Guided by memory, he found the spot where he had buried the tin box more than a decade earlier. He dug in silence until his fingers struck metal. Inside, the paper was brittle but intact, the drawing of the rate error amplifier still legible. He held it to the light, and for a moment he imagined he could hear the faint whir of the radar dish turning, steady, unbroken, eternal. He understood then what the ghost truly was, not a memory of war, but of learning itself the moment a machine, or a man realizes that perfection is never reached, only approached. He placed the paper back in the box and reburied it. The past, he decided, was not to be erased or displayed. It was to be integrated, folded into the circuit of progress, invisible but essential. When he returned to Tokyo, the skyline glittered with the confidence of a new age. Japan had learned the rhythm of precision, yet for Sato, the hum of every factory still carried the echo of that lost trailer in Saipan, the origin point of everything they had become. By 1961, Tokyo had begun to glow. Neon lights traced the skyline like electric veins, and the hum of new factories along the Tama River blended into a single, unending pulse, a heartbeat of a nation reborn. From the rooftop of the Institute of Technology, Professor Yasuji Sato could see it all. The railways glittering with punctual energy, the broadcast antennas blinking over Shinjuku, the cranes building towers from steel more exact than any he had measured during the war. Precision, he thought, had finally become the rhythm of Japan's recovery. But to him, it was more than an engineering triumph. It was a moral correction written in metal and motion. The war's shadow had receded into memory, but not for Sato. He carried it with him in every circuit he drew, in every lecture he gave. To the younger engineers, born after surrender, war was a photograph in a textbook, a static past. But to Sato, it was a living equation still converging. He began each class the same way, by drawing two diagrams on the board. The first, a crude feedback loop labelled unstable system. The second, a cleaner loop labelled stabilized through learning. He would pause and ask, "Which one do you believe we live in?" He had become famous by then not as a wartime engineer, but as the quiet visionary behind Japan's automation revolution. His papers on adaptive control theory were translated into English and cited by American academics who had no idea their author once reverse-engineered their radar. The irony was exquisite, but Sato never mentioned it. When a former U.S. Army liaison, now an MIT professor, invited him to lecture in Boston, he politely declined. "Our feedback has reached equilibrium," he wrote in reply. "It is your turn to measure us." In the spring of 1962, Japan's Ministry of International Trade and Industry approached him with a delicate project, the development of an automated radar calibration system for civil aviation, a system that could measure itself, self-correct, and remain stable without human adjustment. The goal was simple on paper, revolutionary in practice. When Sato saw the prototype's block diagram, he froze. There it was again, the familiar topology of the SCR-584, the feedback amplifier, the servo mechanism, the tracking loop. The machine that had once humbled Japan had now become its template for mastery. He ran his hand along the console, tracing its cold aluminum skin. "It remembers," he whispered. "It remembers everything." The engineers around him looked puzzled. Sato smiled faintly and explained, "Machines evolve as we do. What we once studied in defeat, we now rebuild in purpose. The circuit does not forget, it adapts." That night, he stayed late in the lab. Through the glass window, he could see the calibration antenna rotating against the night sky, its motion smooth and tireless. For a moment, he was back in 1944, hearing the captured radar sweep the jungle air of Saipan, its invisible beam.